Hello and welcome back to Task 6 in the NSA Codebreaker Challenge for 2020. If you've been following along so far, then you know that in the last task we were able to reverse engineer the GPS software on the drone that was recovered in the end of Task 4, and discovered the coordinates of the enemy base. Agents have been able to scan the area around the base and recovered a raw video signal from one of the security drones. We've been told that the signal has already been demodulated, and it's encoded with some sort of Hamming code for error correction, but we don't know what kind of code. Our job is now to determine what kind of code is being used, and then successfully decode the video signal to find evidence that the journalist is still alive. So let's go ahead and get started. We're provided with a file called signal.ham, which we're told contains the samples of the signal stored in IEEE 754 binary 16 values in Little Endian byte order. But before we start trying to decode it, let's get a little bit of understanding of what a Hamming code actually is. Invented in the 1950s by mathematician Richard Hamming, Hamming codes are a family of linear error correcting codes that allow us to encode a signal into special code words that contain built-in error correction features. At the receiving end, these code words can be read and repaired in case of minor errors, and then decoded back into the original signal. In real-world applications, where bits in a signal can easily be flipped by noise, this helps to ensure that the integrity of the original signal is maintained during transmission. The Hamming codes themselves rely on what are called parity bits to detect if an error has happened and be able to correct it. Each parity bit that is added to a block of bits in a signal is assigned to specific bits and is set to either 1 or 0, so that the number of ones in the block is even. This means if a bit gets flipped by noise in the signal, we can tell that there is a problem because the bits don't add up to make an even number correctly. In combination with multiple parity bits, we're able to detect an error and identify the position where it happened. Then we can correct the error before outputting the final decoded block of bits. I'll link some additional videos in the description to go into greater detail in the math behind how all of this works. The first thing we need to be able to do in order to reverse engineer this code is determine the encoding scheme that is being used. This means determining the size of each block, how much of each block is data, and how many parity bits are being added to it. So to figure this out, I'll go ahead and begin setting up a simple script in Python to sort of brute force it. There are plenty of ways that you can load these numbers from the input file, but I'll use NumPy's fromFile function and specify the data type is float16 so it's interpreted correctly. Next, we need to actually conform this data to binary. The numbers themselves are given as log likelihood of value, so any negative number can be set to 0, and any positive number can be set to 1. We don't know how much padding there could be in each block, so I'm just going to loop through numbers of possible block sizes, and then the possible number of data bits inside that block. Then add up all of the data bits and try to convert to ASCII, and see if we see some magic header bytes that will indicate both the type of file and also that we have the correct values. After running the script using the first 200 inputs from the file, we can scroll through the list and see here RIF and AVI, which indicate that the video is an AVI file, and also that the correct block size is 17, and the first 11 bits are the data. As it turns out, there are 5 parity bits, and then 1 extra 0 for padding just to throw us off a little bit. The creators purposely made this a non-standard encoding, so that we couldn't simply be able to use some kind of decoding tool to do the work for us. So now that we know the scheme that's being used, the next step is to determine the parity check matrix that can be used to correct errors and decode it. And the easiest way to do that is to first find the generator matrix for the code. The generator matrix is essentially a specially formulated matrix that allows you to multiply it by a block of input data, and the result is a Hamming code word, meaning a block of 16 bits that contain the original 11 bits of data, and then the correct parity bits set to be able to detect errors in the block. The generator matrix follows a very specific pattern when it is in what's called systematic form, where it's composed of an identity matrix of size n minus k, where n is the block length and k is the number of data bits. And then appended to the matrix is a second matrix A, which represents the parity bits that would be set for that row of input. When an input is multiplied by this matrix, mod 2, then the output sets all of the bits of data, and then the appropriate parity bits for that input to create the final code word, which is in the file we're provided. So if we want to be able to recreate the generator matrix, we simply need to try to find places in the file where these code words occur. However, there are many errors in some of them that throw us off. So I created a simple Python script to basically vote for the correct answers. The idea here is that you loop through all of the input blocks and look for one specifically where there's only one data bit set. Then look at the parity bits. If that set of parity bits has already been seen, we increment the count in a dictionary. Otherwise, we add it to the dictionary. This means that by the time we've processed the entire file, we can see that there are a few places where there are errors, but the correct code words for each row of the generator matrix overwhelmingly receive the highest number of votes. Once we finish processing the file, we simply select the row with the greatest number of votes for each single bit code word, and use them to construct our correct generator matrix. So now that we have the generator matrix, we know how we can put in inputs and get the Hamming code words. But we need the parity check matrix that is used to check for errors to be able to decode the signal correctly. To get this, we can use the relationship between the generator matrix G and the parity check matrix H to construct it. We simply have to take the transpose of the right side of G and then append an identity matrix to the right side, and then set the bottom row to all ones. This gives us the first answer that we can enter into the side for the parity check matrix. Now we need to actually explain what the parity check matrix does in order to be able to decode the video. When a code word is received, it can be multiplied by the parity check matrix H, mod 2, and the output is a vector called the error syndrome. If all of the values are 0, then the code word has no errors and nothing needs to be corrected. However, if there are any 1s in the syndrome, then it lets us know that there is an error in the code word and also the position to help us correct it. Because we have 5 parity bits in this code, we're able to detect and correct up to 2-bit errors in each code word. And to find where the errors have occurred, we can go ahead and pre-compute a syndrome lookup table to make it faster. We simply need to generate all of the possible 1 and 2-bit error patterns for this size of input, meaning every combination of row of zeros with 1 bit flipped, and every combination of rows with 2 bits flipped. We can multiply each of these rows by the parity check matrix H and mod 2 to get the syndrome for each error pattern and save it in a dictionary. After converting the 5-bit error syndrome to a decimal number, we can use it as a lookup index in our syndrome table. This gives us our lookup table so that no matter what the error syndrome we get, we can look it up in a pre-computed table and know which bits need to be flipped to get back the corrected code word. So now comes the final step, actually decoding the video. We simply need to iterate through each of the 17-bit blocks in the input file, strip off the extra padding bit, and multiply the 16 remaining bits with the parity check table mod 2 to get the error syndrome. If it is not a 0 vector, then we look up the syndrome in the table to get the error pattern. Then we can add the original input to the error pattern, mod 2, and that gives us back the corrected data. Next, we take the 11 data bits in the block and add it to our final output. Once we've processed all the code blocks, we can pack the binary data back into bytes and write it to the final output file, which I'm just calling output.avi. Opening that file, we can see that it has been decoded correctly, revealing the security footage of the hostage and a timestamp that we can enter for the second answer. And now we're finally done with phase 1 of the challenge for this year. You can check out the scripts I talk about in the video in the links below, or try to see if you can replicate it yourself and learn how to handle this type of data in the future. We'll be back again soon for phase 2. Happy code breaking!